Welcome to this session. This session is the session about writing AP net ionic equations. This will be question 4 in the free response of the AP exam. We don't know a lot about what that free response holds for us, but we do know that question 1 is equilibrium. We'll spend a lot of time working on that later. And we know that question 4 are net ionic equations. The format has changed in the last few years, and so the intro to this, it needs some editing and some amending, and I'll go through that with you in just a second. But I can't emphasize enough how this is the one thing that you can practice all year long. So I'm hoping that you're hearing this early in your school year, and I'm hoping that you are basically being quizzed on this every month from your teacher, and so I'm really hoping that all of that is true and works out for you. And so let's get down to it. There are about, I don't know, several hundred, well, at least 200 questions and things from the last 30 years that we can practice and play with. So this particular recording is going to focus on double replacement reactions, and there will be other recordings that focus on other bits, but I promise you this one, I can't get all of the examples done in one sitting, nor would you want to listen to all of them in one sitting, because at some point you sort of get like lulled into a coma. So we're going to go through, maybe 10 or 12 at the end of learning how to write them, period. And then there'll be some other files that you can just cut to the chase and go and see how each one of them is worked out. And there will be some repeats. This particular document came from, I need to give credit where credit is due here, a fabulous AP chemistry teacher named Kristen Henry Jones. Ms. Jones teaches at A&M Consolidated High School in Bryan, College Station, Texas, and essentially it's the high school that is closest to the campus of Texas A&M University and our beloved Texas Aggies. So Kristen did a fine job with this, and I have never felt the need to rewrite it. I know I could have never done as good a job as she did. But this first part was from prior to 2007, and so we need to sort of make sure you're aware of how the test is formatted. So she opens by saying that AP equation sets are found in the free response section of the AP test. That is correct. It's going to be question 4. So the minute that the proctor has wrenched your calculator from your grasp, since you have your calculator for questions 1, 2, and 3, the next thing that happens is you open up the second half of your testing booklet, and this is the question that will be facing you. So I want to put you in attack mode. I want to make you strong enough that you just go, no problem. It's a 15-point question. It's the only 15-point question on the exam, and I want you to go forth and conquer it. Hopefully all year long you're going to make 10-ish points or better. I would love it if you walk into the exam with a personal average of somewhere between 13 and 14. 15 is a little tricky, but you may can pull it off. Last year's set, I have to say, was exceptionally easy. And you'd have probably been going, why did I work so hard? That set was easy. Well, that does not bode well for this year's set, I'm afraid. So let's get to it. The truth is you are given 3 equations, and you must answer them all. Answer all of these, no choose. And the equations are of mixed types, and the set is worth 15 points, and I'm not sure about these percentages right now, so don't worry about it too much, but 15 points is a big deal. So you want to make sure that you get as many of those 15 points as you possibly can. The nice thing is that all of these AP equations work, meaning that the chemistry really does happen, so you don't have to think about that. You just assume a reaction will take place. You do not assume that we are trying to see if you know that if it's a soluble substance mixing with a soluble substance, and according to all solubility rules, the 2 products would also be soluble. That's just no fun at all chemically. So these all do really make something new and different. In each case, in other words, a reaction is going to occur. So they need to be written in net ionic form. And you should have already listened to the recording, or at least been taught in class, how to do basic net ionic equations. So what I will tell you, and this is good news. I know I don't always deliver good news, but this is good news. You don't have to do it the way you initially learned how to do it, which was write the molecular equation the way you wrote it in Chem 1, identify all the spectator ions, write everything ionically, identify the spectator ions, cross out the spectator ions, and then the third step would be to write a clean net ionic equation. You can just go straight to the clean net ionic equation and save yourself loads of time. You also don't have to worry about the little AQs and solids and liquids and such. They're nice if you have habits of putting those in, that's great, but it's not necessary. So what's important here is that all of the spectator ions must be left out, and all ions must be written in ionic form. So all molecular substances, those would be those covalently bound substances that do not ionize, and any non-soluble compounds must be written together, definitely not ionized. And the only way you understand what you're supposed to do when is because you know your solubility rules. That's not negotiable. You should have started learning them in first year and hopefully master them any day now. So there's just some unique and special things that you sort of have to give up and just know. Calcium and strontium hydroxides are moderately soluble and can be written together as ions. Barium hydroxide is soluble, but magnesium hydroxide is insoluble. So let me just kind of make that a little simpler. Look at the 2A metals. Here they are, right here. The big scoop is when you're talking about hydroxides of the 1 and 2A metals are strong if they dissolve. The issue is these two little guys up here at the top, the two little guys, they're so small that they don't dissolve very well because their nucleus, which is the positive center of the atom that's holding on to the electron of the bond that's going to be formed between themselves and the OH group for the hydroxide group, they're so small that that bond is really strong. When you start shielding that nucleus with a whole lot more electrons, notice the many, many, many more electrons as we go down the periodic table, these become much more soluble. Calcium's kind of on the fence, but what you remember is that of that strong bases that ionize are 1 and 2A metal hydroxides, but there are solubility issues with these little guys, so we always write them together. Alright, so calcium sulfate and strontium sulfate are also moderately soluble but can be written as either together or as ions. So that means you just don't have to worry about that statement. Just don't worry about it. If you put them together, that's fine. If you write them as ions, that's fine. Don't worry about that. So weak electrolytes, such as your weak acids like acetic acid or any other acid that's not in your list of strong, are not ionized, so we write those molecularly. Solids and pure liquids, this is big. Solids and pure liquids are written together. You don't have to worry about solubility rules at all. That's a smiley face. You don't have to worry about solubility rules, just write them as a molecule. A saturated solution is written in ionic form, while a suspension is written molecularly, where the things are written together, because how do you know visually you have a suspension? Solid is present. Saturated, you don't see solid. You click from saturated, which is holding as much solute as possible, over to suspension the minute boom, you can see some solid. I know you like my sound effects. Alright, so AP equations do not need to be balanced as a lie. Big, giant lie. Because the format change that occurred was that now we have to balance them. But that is the best news for you. Again, I bear good news. Because you get a point for balancing. So for the love of God, whatever you write, make sure it's balanced and you're going to get a point unless what you wrote is completely ridiculous. So you must waste your time on balancing. It's worth a point. Each equation is worth a total of 5 points for you. 1 point is given for the correct reactants, and that's a set, so correct set of reactants. And 2 points for the correct products. If a reaction has 3 products, you're going to have to get 2 of them correct for 1 point. And then if you get all 3 of them, that's when you'll get your second point. Leaving in the spectator ions is a really bad idea because it's going to result in many, many missed points on the equation set. So leave the spectators out. The best way to prepare for this is twofold. First of all, practice, practice, practice. I encourage AP Chemistry teachers to give a quiz on this the first class period of every week once this whole thing has been taught. Many quizzes while teaching it, but once a week, every week, the rest of the school year. And I do the same with first year chemistry teachers, the same with formula writing and naming. These are just practice skills. It's like you wouldn't, if you were a piano player, you wouldn't not practice for a year and then expect to give a concert. So this is something you have to practice. The equation sets are kind of similar, and some equations show up year after year, and you'll get to see that when you start seeing all these repeats. But there are patterns, and I want you to be looking for patterns. I want you to be a bit smart and lazy. And people who are smart and lazy embrace patterns and can apply the patterns across a lot of different details, shall we say. So when you're reading an equation, first step is to try to classify it by type. So we're going to go through these by type. By type, I mean double replacement, single replacement, anhydrides, redox. We're going to do this by type. If it says anything at all about acidic or basic solution, it's acidified, it's alkaline, it's code for basic, then it's going to be redox. And if you're totally stuck, just look up the compounds in the index of your book when you're practicing or other reference books and try to find information that's going to help you with the equation. But all reactions do not fit neatly into just one of the 5 types of reactions that you learned in Chem 1. You're going to learn a whole lot of things are redox and combustion, stuff like that. So save the reactions that you write, and you want to practice them again and again and again before the AP test in May. Also, there is a reaction site. This is a practice site. Now this practice site is in the new format. And again, the new format is 3 equations, balance it, which is different from the way it had been done for like 25 years prior, and answer a descriptive question. Examples might be, what would the pH be of the solution? What color would the solution be? Explain a laboratory test that would confirm the presence of oxygen or the presence of hydrogen gas, things like that. So this site right here, I know it's not a friendly URL, but UNL stands for University of Nebraska at Lincoln. EDU is obvious for education. David W. Brooks is what that part stands for. I don't know what the 4 stands for, and I suspect this was his second attempt at this and second version. But this is just a periodic table that has that site on it, so I just use this as a way to give you that URL. Write it down, bookmark it, use it often. If your teacher gives you a quiz every week and say the first class period of every week, kind of some of you are on blocks where it might be a Monday, it might be a Tuesday, it might be a Wednesday after a holiday or something, I would go there that night before and I would practice a few before I made a bad grade. So a couple of different ways to deal with this. I don't know which copy I was working on. I think it's that one. Okay. Sorry about that. Had to find my spot again. All right, so we're going to deal with double replacement, which I got to tell you, until I started teaching AP, I had never heard the word metathesis in my life. I don't know if that's an old word, but I got to tell you, none of my professors ever used it. But if it says something about a metathesis reaction, then it's talking about a double replacement. You remember double replacements. Double replacements is when you have 2 compounds, and they're going to probably be soluble in order to make this happen, and we're going to swap partners, is what it essentially boils down to. You know, like AB reacts with CD, and what would it make? So I always reminded my kids that the algebra teachers, whenever you took Algebra 1, do a really good job of this method with factoring and such called FOIL. First by the first, outside, inside, last. So we're dealing with the OI, the OI of FOIL. And so I want to do the 2 insides together, which would be C and B. Why isn't it B and C? Because normally we write, you know what that means, right? There's some exceptions. But normally we write the positive oxidation on the left and the negative oxidation on the right. So when I put these back together and I take these 2 together, I need to write the positive on the left and the negative on the right, and then AD, the outsides. So that's the general format of double replacement. I know I just insulted your intelligence because I'm certain that you knew that. So no changes in oxidation numbers occur. So you want to be on the lookout for that. No changes in oxidation numbers occur. But all of these reactions must have what we call a driving force. And that will not be the last time you hear me say that. The driving forces, we're going to go through each one of them that are most common, are the things that is chemically pushing this reaction to make and break bonds. So what happens is that when this occurs, we often remove a pair of ions from the solution. So number 1, first and foremost, is the formation of a precipitate, hence the need to know your solubility rules. So a precipitate is simply an insoluble substance formed by the reaction of 2 aqueous substances. That's why I said most of the time your beginning reactants are both soluble. And that doesn't mean their ions will all participate, but they're usually soluble. And a precipitate is an insoluble substance that's formed by the reaction of the two aqueous substances. So two ions bond together so strongly that the water cannot pull them apart. When water hydrates each ion, surrounds it, gangs up on it, and tries to attract them away from each other, no, the water can't do it. It's just overpowered by the strength of that bond. So you must know your solubility rules, like I said, over and over and over again. So here's a good example of how this would come at you. Notice, all words. So solutions of silver nitrate and lithium bromide are mixed. Well, I know my solubility rules, and I know that all nitrates are soluble. All nitrates are soluble. So there's no way that, even if I make lithium nitrate, it's definitely going to be soluble. So these are just a spectator ion. And also, I'm happy that it said solutions. I didn't have to think about are solids or gases present. We'll get to more of that in a minute. And then, so what would I make? I also know that all 1A metals are soluble. And I realize that you do not have the periodic table memorized, but you do have one handy. If you don't, I'll wait. Go ahead, pause me, get one. But here's lithium right there in the 1A's. So I know good and well that that's soluble. So the only thing that can be made is silver bromide. And I had a solubility rule for that too. Compounds of silver, mercury, and lead are what I call the heavy metal bad guys. And halides, which is bromine, again with the periodic table, there's bromine. So these are the halogens. So halides are the negative ions of the halogens. The halogens would be F2, Cl2, Br2, I2. But when they ionize, F minus, Cl minus, Br minus, and I minus. So those particular critters are soluble except when they are with silver, mercury, and lead. So indeed, I write down then what is it that is reacting? The ion of silver and the ion of bromide. So check, check. And what happens? We make a solid silver bromide. If you choose to, you can do that to indicate it's a solid. You can do that to indicate it's a solid, or you can just leave it alone. Your call. So that's the first driving force, precipitation. The second is forming a gas. Now these get a little trickier. You got to know a little more. You got to know more than just your solubility rules. There's a couple of patterns that are going to be your friend. Gases may form directly in the double replacement reaction or can form from the decomposition of products like carbonic acid and H2SO3. So when carbonic acid is formed as a product, go immediately to H2O and CO2. And when this is formed as a product, you go immediately to H2O and SO2 as gases. So in other words, to get these to be acids in aqueous solution, we have to bubble a gas through water. So the minute you take the cap off and you're no longer keeping that solution under pressure of sorts, then these gases, which I can do an up arrow for gases, bubble right on back out. So excess hydrochloric acid is added to a solution of potassium sulfide. Oh, 1A metal. Oh, a halogen. Wait, is silver, mercury, or lead present? Nope. So I can get rid of the chloric and just think about it as H+. And then I already got rid of the potassium, so my sulfite is SO3 2-, and you should know that. Shame on you if you don't. So it's my H+ and my SO3 2- that are reacting, and my inclination is to just smoosh them together and make this, but you must make effort to memorize that these two critters behave this way. Notice the pattern, H2CO3, H2SO3. H2CO3 and SO3. So they're over here on the nonmetals. So it's even possible that we may have the same sort of thing happening with other compounds as well. A solution of sodium hydroxide, I celebrate that 1A metal and get it out of there. And ammonium chloride, that's also very soluble. So when these things are added to solution, I'm going to make sodium, ammonium, and wait, let me think that through. Oh, but it's the chloride here that's not going to be reacting. So let me try that again. Sodium, out of there, no problem. The hydroxide is going to be added to a solution of ammonium chloride. Well, sodium chloride is very, very soluble. So I can get rid of both of those. So what I really have is the ammonium reacting with the hydroxide. There's my hydroxide, there's my ammonium. This is how we make ammonia gas. So that's going to be given off as a gas, and the remaining thing is going to be water. So if you ever have your chemistry, if you've ever been around when your chemistry teacher pulls out their nice big jug of ammonia, that's what we colloquially, I have a hard time saying that word, call it. It's really not ammonia that's captured in the bottle, because ammonia is a gas at room temperature. You're seeing a liquid at room temperature. So what it really is NH4OH in solution, in aqueous solution. And if you've ever been around when the bottle has been opened, you become painfully aware that it immediately decomposes into this. And that's why we write this way. So stinky, 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 stinky ammonia comes out of that bottle the minute you uncap it. The third driving force is the formation of a molecular substance. So when a substance such as water or any weak acid like acetic acid, there's any acid that's not in our list of 6 is considered weak. So when that is formed, ions are removed from solution and the reaction actually works. So dilute solutions of lithium hydroxide and hydrobromic acid are mixed. So I'm thinking HBr, that's a strong acid, so that means it exists this way. And I have a 1A metal, so that's not going to participate. So what is it that's actually taking place here? My halogen, again, is going to be a spectator, so the bromic part of this leaves only H plus to react. This is what you lay in bed and pray for the night of the AP exam. Strong base, 1A hydroxide, strong acid in my list of 6. The net ionic equation is simply H plus plus OH minus yields water. They actually gave that on the test last year. Don't expect it this year. So again, you need to know your 6 strong acids, and there's half of them. Back to the periodic table. This one, fluorine, again, it's kind of the same story as these 2 little guys over here. Not strong because they're not soluble. Not strong doesn't mean it's not dangerous. It will eat the calcium right out of your bones, and an amputation will be in your future if you ever spill HF on your body, which is why we do not put that in a high school chemistry lab. So this is the weak acid in terms of HF, but boom, 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 there's half of your list of 6. Hydrochloric, hydrobromic, hydroiodic. So gaseous hydrofluoric acid, must recognize that as being weak, and it will be written molecularly as HF. Reacts with solid. I don't have to think anymore. I just write the formula for silicon dioxide. Solid is my friend. Solid says, hey, not soluble. So you don't even have water present. It's not even in solution. It's just a chunk of silicon dioxide. So you simply write HF plus SiO2. Then you have to figure out insides and outsides. So Si, F4. How do I know it's F4? Well, I'm sure you already do this, but if you don't, it's an excellent practice here to, the minute you get a clean periodic table on any exam, there's several things you should write, and this is in Adobe, so I don't know how well this is going to work, but I'll give it a shot. +1, +2, +3, plus or minus 4, plus, oops, sorry. Oh yeah, how do I erase? Forget that little scratch out right there. Oh, there's a way to relate. Yeah, delete. Ah, that was more trouble than it needed to be. This is going to be -3. Are you seeing a pattern? +1, +2, +3. Ooh, wishy-washy. Plus or minus 4. -3, I'll bet you can guess. -2, -1. And rarely would you ever have a noble gas even reacting. It does happen, but it's very, very rare. So this is the most common oxidation state, most generalized oxidation state. It ain't everything. It's not the total picture, because that'd be way too easy. But I know that here sits silicon, and if it's going to be negative, it's often a -4. Let me also say there's more than one right answer to most of these. So you could have used even a negative or a +2 for your silicon and gotten away with it. But SiF4 would probably be the most common and most widely accepted with most texts. So, and then when hydrogen and oxygen get together, we make our good buddy water. Don't be afraid to make water. Water shows up in a lot of these equations as either a reactant or a product. All right, so I've talked about solubility rules, but here's a nice abbreviated, very visual, easy to remember sort of set of these. So I've got the strong acids, HCl, HBr, HI. That's my little trio that's on the periodic table. Remembering the little guy, HF, at the top of the halogen column is little, therefore it's got a very strong HF bond, and water alone cannot break it. Then we have sulfuric acid, which is our only diprotic acid, 2 protons, 2 H's. Nitric acid, which is oxidizing acid. meaning we often use it to dissolve metals. And on the AP Chemistry wiki page, AP Chemistry nimsy.wikispaces.org, or sorry, not org, that's my email address, .com, which is probably how you got to this video in the first place, has on its homepage right now a cool little video of the Ira Remsen demo. It's really quite clever. And if you'll watch it, you'll never forget that nitric acid is the oxidizing acid that will dissolve metals. And it was a penny that Ira Remsen sacrificed to learn his chemistry lesson. The strongest acid of all, because it's got 5 very highly electronegative atoms pulling against the bond that H has with that oxygen. All of these that have oxygen, the H is bound to the oxygen. I know, it's kind of annoying that we write it as if it was maybe bound to the N or the Cl or the S, but make no mistake, they're bound to one of the oxygens. So it's very easy for that bond to break in water. And so this is the strongest of the group. Again, we won't let you play with that in our lab. There's not a high school lab around that should have that in it. All of these things you must memorize, 6 of them. Big whoop, 6, right? HCl, HBr, HI, sulfuric, nitric, perchloric. Those will always be written as ions. They're 100% ionized. Anything that's not in this list that is an acid, you write molecularly. Do not ionize it. Strong bases are hydroxides of group 1 and 2A, where calcium is marginal. Barium and strontium are okay, but definitely the 2 little guys, beryllium and magnesium, are weak, which means you write them this way, no matter what. And then these things are always soluble if in a compound. Nitrates, group 1A metals, ammonium ion metals, or I'm sorry, not metals, compounds containing the ammonium ion. Anything that has acetate, perchlorate, or chlorate, or chlorate. No exceptions. This is what I call the Big Mama rule, because it governs everything. If these things are there, then you want to always be on the lookout for these things, because they make your life so much easier because there are no exceptions. Halides are soluble except the heavy metal bad guys, silver, mercury, and lead. Silver, mercury, and lead. Heavy metal bad guys. You'll see me write that from time to time. And then sulfates are generally soluble except for the heavy metal bad guys and calcium, strontium, barium. Again with the patterns, calcium, strontium, barium. These heavy guys over here on this portion of the periodic table. I wish I had a magic pill. I'd be rich, actually, if I had a magic pill I could just sell in the drugstore that says, here, take one of these every day and your solubility rules will just automatically go into your brain. Wish I could do that. I cannot. You're going to have to work at this. If it does not fit one of the 3 rules above, then just assume it's insoluble or a weak electrolyte, but either way, you write it together molecularly. You do not ionize it. And I'm just telling you right now, it's not going to always be correct. That's why it's really hard to get 15 points on this, because you have to know way more than what fits in that little chart. But it's going to cover most of the situations, and you're going to get 13, 14, 15 points without any trouble. Also, these words are your best friends. Anything that implies gases. So if bubbles are mentioned, if vapor is mentioned, anything you can think of that remotely means gases, then you don't have to worry about your solubility rules. You just write down the molecular formula. If it says liquid, not to be confused with aqueous, not to be confused with solution, but if it says liquid, liquid bromine, something like that, again, you don't have to worry about your solubility rules. Many, many words that mean solid, but if it says solid, again, it's a relief. I don't have to worry about my solubility rules. I just write that puppy's formula down. So remember that these are 3 things you must commit to memory. We already talked about this. Carbonic acid decomposes right away into H2O, and CO2. Ammonium hydroxide we've talked about. When you open the jar, stinky, 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 because it makes this ammonia gas and water. And H2SO3 does what carbonic acid does. It makes the SO2 gas and water. So there's a pattern there. It's not terribly awful to remember. All right, so we're going to see how much of this we can get through before I think both of us get tired. So off we go. There are many ways that you may have been taught to do this, but this is just the way that I like to do it because I'm lazy. That's just, you've heard me say that before. But I just mark on the actual words here thinking about my solubility rules and reading the words, what needs to happen next? I realize initially you're taught to do 3 steps. I did that in the recording that went with what's typically chapter 4 that was called Net Ionic Reactions in the lecture notes for lecture. But this is, you should have already been there and done that. So we're going to speed this process up, and we're going to make this more streamlined, because you should not spend more than 10 minutes doing 3 of these equations and answering the little question that goes with them and balancing them and the whole bit. I'm not giving you the current format of the AP exam. I want to be very clear about that. I have reverted back to the 30 years worth of the sentences that tell us what to do with the net ionics. We're going to get really good at that and balancing first, and then your laboratory experiences should help you with the little easy question about each one. So off we go. Hydrogen sulfide is bubbled. Oh, bubbled. What does that mean? It's a gas. That means I don't have to worry about solubility rules. Just write down a formula for something with hydrogen and sulfide. Sulfide is sitting over here in the -2s, and hydrogen is a +1, so I must need 2 of those. Basic formula writing. Is bubbled through a solution of silver nitrate. All nitrates are soluble. It's only the Ag+ that I'm concerned with. So what is this going to make? Well, the only thing that can happen is that silver ion bumps that hydrogen out of that compound to give me H+ and take its place. And since it's also a +1, then it's going to be Ag2S. Again, I say that's a -2 because of its position in the periodic table. You should have learned a long time ago that silver makes one and only one ion, and it's +1, which is why silver, cadmium, and zinc don't use Roman numerals. So silver, I put them in alphabetical order. The first one's 1, +1. The other 2 are +2. But I've got to remember silver, cadmium, and zinc. That's just my way of remembering it. Get your own way if you don't like my way. All right, so now I need to balance this puppy. I see a 2. I see a 2. I need a 2. And I need a 2. That's a point. So let's decompress how this works. The fact that you wrote H2S and Ag+ is worth 1 point as a set. If you left the plus off of Ag, no points. If you didn't put the 2 on the H, no points. This is a yeah or a no. You either get it and you get it all correct, or one little error loses that point. Then we only have 2 products, so we get a point for each one, and then we get a point for balancing. I want to reiterate one more time, that set of reactants has to be exactly correct for you to earn that point. Same here. If I'd left that plus off, if I'd have left that 2 here off, this 2 was just me explaining to you, but I would be careful with your chemical formula writing skills. Beg for some quizzes if you need help with that. Go to the internet. There's lots of cheesy little sites that will give you the name of a compound, and you put in the formula, and you can hone those skills if you're weak on that. All right, so then this would be 4 points for just doing that. And then, like I say, now there's a little question that would go with it that might ask you, how would you separate the product, or what would be the pH of the solution? Well, if you got excess H+ running around, it's going to be an acidic situation, so it would be less than 7. Things like that. We'll worry about that later. We're just going to get this skill down first. An excess of sodium hydroxide, 1A metal, is added to a solution of magnesium nitrate. All nitrates are soluble. What's left standing to react? OH minus, Mg2+. That would make MgOH twice. Mg, 2A metal, one of the little guys, never going to be ionized as a product, never going to be ionized as a reactant. If it had said magnesium hydroxide, I would write that as MgOH2 as a reactant. But the fact it said sodium means I'm good, because it's a 1A metal, definitely strong. So there you have it. Now you have to balance it. So what you going to do? See that 2? Start there. I need 2 of those. Resist the urge to get creative. Everything is balanced. Again, 1 point. Now there's only 1 product this time. It's more important than ever that you get it correct, because you'll lose 2 points if you don't know it's MgOH2 rather than just MgOH. So 2 points, 2 big ones for that, and a point for balancing. I'm not going to do this on all of these. I'm just trying to get you started. Okay. Now, it's time for you to pause and try some of these on your own. I realize that you get some of these for homework assignments. And I realize you may be tempted to just come out and listen to this and just write down the answers and maybe get a grade. But I'm also going to tell you that if your teacher has ever crossed paths with me, they're going to quiz you. And if you don't know how to do this, you're going to suffer. My students took a quiz the first class period of every week on this from the minute they learned how to do them. Sometimes while we were learning to do them, they took a quiz a day. And they figured out really early that if they would quit being stubborn with their solubility rules, and if they would study just a little bit and use that website and practice just a little bit, that they could make 100, 100, 100, 100 instead of F, 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 F. Because there's usually not a lot of grades in between. Because you either know how to do this because you know your solubility rules and you can write formulas and you can balance equations, or you don't. It's not hard stuff, but it is something that you have to work at. It's not going to just like land in your lap. All right, so solutions of sodium iodide, get that 1A metal out of there, and lead nitrate, get that nitrate out of there. So that leaves me with iodide, not iodine, read carefully. Iodide is an ion, ide endings are ions, and lead, and this is going to be an ion because it's a solution, are mixed. No choice but to make PbI2. How do I know it's PbI2? How do I know it's lead nitrate? Well, lead only comes in two varieties, +2 and +4. So another equally correct option. This is why I said some of these have multiple answers. And I'm not going to give you all of them. I'm just going to give you the most common ones. So if you're ever curious, you should ask your teacher. Like if you get a paper back and you're like, but I did this. Isn't this also correct? The answer is yes. This is also correct. So when you balance, what must you do? I need 2 of these for this to be balanced, and I need 4 for this to be balanced. Either way, we got a winner. And I know that halides are soluble, except the heavy metal bad guys, and lead is one of them. Again, I remind you, there's silver, mercury, and lead. Silver, mercury, and lead. Silver, mercury, and lead. Say it over and over until your brain hears it and files it. All right, so next we have a solution of ammonia. Okay, ammonia is a gas. NH3 is added to ferric chloride. So a solution of ammonia is going to give me NH3 and water. Now, this could also be written the exact same way to say a solution of ammonium hydroxide, or it could just say ammonium hydroxide is added to a solution of ferric chloride. But ammonia is not going to exist in aqueous solution. It's going to exist as the gas and water separated from it. So ferric, now this is an old one, old. My kids would struggle with this. There's us and there's ic. And the ic has the higher oxidation state. So ferrous chloride is old terminology. That would be Fe2+. Ferric is Fe3+. Take a moment and appreciate the beauty of the newer system that you've been taught, which is the Roman numeral system. Because these days, this would have been written as iron. Forget the ferric business. Roman numeral 2, or well, this one would be 3. Chloride. And that 3 is telling you this is a +3. So I know that's a +3, but you might not have, and I can forgive you that. What are we going to make? We're going to make ammonium ions. And we're going to make, because what's going to happen is this water is going to split. Think of it that way. And so the H+ is going to come over here and attach and make your good buddy, very familiar, only +1 polyatomic ion, you know, ammonium. And that means I'm going to make FeOH3. And a lot of hydroxides are insoluble. So I know if I've got a metal that's not part of alkali or alkaline earth metals, that I'm most likely going to make a precipitate with that hydroxide. Well, I am going to make a precipitate with the hydroxide. Not most likely, I just flat out am. All right, so is this puppy balanced? What do we need to do to balance it? This one's a little more challenging to balance, isn't it? I've got, first of all, I have 3 O's. Let's start there. See them? 3 O's. So the only source of O's on the left are right here. And then I've only got 1 iron on each side, so that's pretty cool. And what must I do now? I need 3. Do I need 3 NH4s as well? Let's see what we've got going on. 6 H's and 3 more H's. 6 H's and 3 more H's is 9 H's. If I double this, what am I going to get? Well, let's go to 12. 3 times 4 is 12, and that means I would have to do this. That's 9, and 6 is 15. I have a mess on my hands here. I don't think I can balance this. What's wrong? Start again. Oh, okay. And then start here. Here's what I'm doing. I have to balance the charge in this. So this 3 plus neutral and neutral going on over here requires that I get 3 pluses by putting a 3 there, which then requires that I get a 3 over here on this nitrogen. So now I have 3 times 3, which is 9 H's, and I'm going to need a 3 here to get my O's for that hydroxide, and so that's going to give me 6 more, and that's going to give me 15. And I've got 12 and 3 on the H's now, and that's 15. Yes. All right, so let me back up and do that again, because we haven't talked about this. For an equation to be balanced, a quickie check is, are my charges balanced on either side of the arrow? And if you're not good with that, you might want to listen to the redox recording and review redox equations, because that's how we know they're balanced without being real tedious with counting every N and every H and every O. So my first clue was charge on the left is +3, charge on the right is +1. I need to triple that, and I let that be my starting point. When I tripled this, I got 3 N's. I need 3 N's. So I went here, from here over to here, and then I dealt with the H's last because I've got 2 different sources for them, but I looked at the O's. So I have 3 O's over on the right and only 1 on the left, so I need a 3 there. So 3 times 3 is 9 H's, plus 3 times 2 is 6 more H's, for a grand total of 15 H's. Lucky for me, that's what ended up over here. 3 times 4 is 12 H's, and 3 more H's is 15 on each side. Check, check. 1 iron, 3 N's, 3 N's. I'm done. So that one took a little longer, but we get one. That's a lot to do for 1 point, is get ammonia, water, and iron 3. And then ammonium would give you a point, and iron 3 hydroxide would give you a point, and then you just have to get it balanced for that last point. So that one was a lot more work than the ones we've done so far. Not my favorite, I gotta say. Solutions of silver nitrate and sodium chromate are mixed. Okay, they're going to make up for it here. Silver nitrate, boom, nitrate's out of there. 1A metal, out of there. So what have I got? Ag plus and CrO4 minus. And if you don't know that, for shame. For shame, for shame. So what am I going to make? Well, it's a heavy metal bad guy. It's most likely going to make a precipitate. So I would need 2 of those and put that with my -2 polyatomic ion. And then balance. I'll need 2 of those. And I'm done. And I want you to also note that the total charge is balanced on each side. 2 pluses and a -2 is a big fat 0. And this is a neutral compound, a big fat 0. So that's the last step, is you want to always check that before you leave it as quote-unquote done. Excess silver acetate is added to a solution of trisodium phosphate. Again, this is kind of old terminology, but it's the kind terminology, because that's going to be NaPO43, but either way, it's out of there because it's sodium. So when a metal out of there, I don't care how many of them there are, and acetates are also all soluble in compounds. So I'm left with Ag plus and PO43 minus. If you don't know that, again, for shame. I cannot help you memorize your polyatomic ions. So I'm going to put that together, and since I have a 3 minus ion and silver is a +1, I know I make this, and to balance it, what do you figure? Yep, there you go. All right, here's a Roman numeral one that is just a celebration for me, because I already know that's a +2, because that's what this 2 is telling me. Nitrate's out of there, sodium's out of there, so Mn2 plus OH minus yields the only thing it can yield, MnOH2. Balance. Need 2 of those. Total charge on the left, 0. Total charge on the right, 0. I didn't do that up here at number 6. Total charge on the left, 0. Total charge on the right, 0. If you do that, you're more guaranteed to have it correct. I've never had it fail, but never say never, in chemistry in particular. Okay, moving on along. A saturated solution, again, let's think saturated versus suspension. This means I don't see any solid yet. So this word is nice, but it doesn't give me any help. Of calcium hydroxide. Okay, calcium hydroxide is on the fence. So you can write it together or you can write it apart. It doesn't matter. You just got to write calcium hydroxide. It's added to a solution of magnesium chloride. So what's going to happen here is my chloride is a spectator, and when my calcium is released, I would make calcium chloride. So I'm going to write Mg2 plus OH minus yields MgOH twice. So 2 of these, and I'm done. Total charge on the left, 2 plus 2 minuses is 0. Total charge on the right, 0. All right, moving on. I'll do a couple more of these before I cut to a new recording. Hydrogen sulfide gas. Woohoo, gas, yay, H2S. I don't have to think about solubility rules. I just need to think about that sulfur is right here in the -2 column, so it needs 2 H's, and it is a gas. I'll do that to remind you, but you certainly don't have to do that. Is added to a solution of cadmium nitrate. So you still kind of contemplate what's going to happen here. Am I going to make cadmium sulfide, and hydrogen nitrate would be HNO3, which is a strong acid in my list of 6, so that nitrate is indeed a spectator. So I'm just going to pick up the cadmium ion and do the only thing I can do, which is swap out and make CDS plus 2 minus 2, CDS, as my solid, and then that's going to give off 2 H pluses. It's not going to give off hydrogen gas. It's going to give off 2 H pluses. If you wrote hydrogen gas, you missed it. Because if I take the hydrogen sulfide and bubble it through water, I'm going to make a weak acid. So that's why I knew that's what was going to happen. All right, dilute sulfuric acid. That's a strong acid. It's going to exist as H plus and SO42 minus because it's in my list of 6. Is added to a solution of barium acetate. Acetate is out of there, and so I got to think about this as H plus and SO42 minus. I should have switched to blue. Sorry about that. So what am I going to write? I'm going to write H plus SO42 minus because that is strong. Therefore, it ionizes. I can always cross it off if I've goofed and want to later. And then I'm not going to use actually I have to write it all out this time. The barium and the acetate. I should not have crossed that off because when I got down to it, I'm like, I know I'm going to make barium sulfate, but you know what? This is going to recombine with the H plus over here, and that's a weak acid. So it's written as a molecule. Oh, arrow. So insides, most sulfates are soluble except for that Big Mama rule that overrides everything. And that's plus 2 and minus 2, so that's the correct formula as written. And then HC2H3O2, acetic acid. Again, I say, I know my 6, hydrochloric, hydrobromic, hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and perchloric, and acetic acid is not one of those, so it's weak. All right, let's do 2 more, and then we will end this recording, and if you are a glutton for punishment or still not getting it, you can come back for more. But you better work some of the examples before you come back for more. So a precipitate is formed when solutions of trisodium phosphate, that sodium's likely to be out of there, yep, sodium's out of there, and calcium chloride are mixed. So the chloride's out of there because I'm going to make sodium chloride, and we know that's soluble. So all I got going on here is Ca and phosphate. Oh, a little more fun with our formula writing. A 2-3 trick. When you got 2-3 trick, you got to have 3 of the 2s, 2 of the 3s, you got to go to 6. So Ca, I need 3, and phosphate, I need 2. Now, what's that going to do to our balancing? Same thing, it's still a 2-3 trick. I need 3 of the 2s and 2 of the 3s. And that makes a total of plus 6, plus minus 6, which is 0 on the left and 0 on the right, and I'm feeling good about that. Did I balance that one up above? I don't know that I did. Yep, I think I did. Actually, I need 2 of these and 2 of these to balance it, don't I? Let me think this through. Over on the left, I have a +2 and a minus. No, I don't. I almost talked myself into that. Everything balances out to 0 up there. So that's why I didn't stop and balance it, I guess. My brain knew that. And then I tried to talk myself out of it. That means I'm getting tired, so it is time to stop. So let's look at number 12, and we're done. And I'll put Lucky 13 on a new recording. A solution of copper 2 sulfate is added to a solution of barium hydroxide. So barium sulfate is a classic precipitate. If you do enough of these, you'll start to figure that out. And in the case of this hydroxide, my strongs, which are ionized, are 1 and 2A metals, of which copper clearly is not, because it sits right here in the transition metals. So I'm going to ask myself, is copper 2 sulfate actually soluble? And it is. Most sulfates are. Barium and hydroxide. And now just do your insides outsides. Barium sulfate, definitely not soluble. Sulfates are pretty much soluble, except, back to the periodic table, barium, strontium, calcium, that little trio right there. And so, like I say, the calcium sulfate and barium sulfate show up quite a bit, but barium sulfate shows up a lot in these equations. And then outside I have copper 2, which requires 2 hydroxides. And most hydroxides are insoluble except for 1 and 2A metals, and then even the little 2 guys at the top of the 2A's are insoluble. So am I balanced? Yes. I need 2 of these, and we're done. Yep, total charge on the left now is 0. Total charge on the right is 0, so we're balanced. So if you need more practice, come on back. I'm going to call this net ionic double replacement 1, and there will be a 2 and even a 3, because I got to tell you, over the last 30 or so years, I've only accumulated 43 examples. So we've got more work to do if you need to. If you don't, then have a great day. Thanks so much. Glad you were here.